In this video, we'll explore the third major stage in training large language models, training the neural network. Let's dive in. At the heart of a large language model is a deep neural network based on the transformer architecture with billions of parameters, also referred to as weights. Think of them as numerical settings that determine how the network processes input, sequences of tokens, to produce output, predictions for the next token. LLMs employ complex mathematical expressions that combine input tokens with these parameters to make predictions. Once the internet text has been pre-processed and tokenized into a massive one-dimensional sequence, the next critical step is training the neural network. Training means feeding it a huge amount of tokenized text from the internet and teaching it to predict what comes next, what token at a time. As it goes, the model adjusts its internal settings to get better at spotting patterns and understanding how language flows. This is where the model learns to recognize patterns in language by predicting the next token, and where most of the computation happens. As the model trains, it repeatedly adjusts these parameters to better predict what token should come next. Each prediction is compared against the actual next token in the training data, and the model updates its parameters to reduce the error. This process is called optimization. Over time, by spotting patterns and learning how language typically flows, the model becomes better at generating meaningful, coherent responses. The process begins by taking small windows of tokens from the tokenized dataset. These are sampled fairly randomly. The window size can vary up to limits like 16K, 74K, or 128K tokens, depending on the model architecture. Very long windows are expensive to compute, so practical limits are set. Let's take this example sentence. I enjoy eating pizza with my family on Monday afternoons. And we take a window of 4 tokens. I enjoy eating pizza. These are the tokens for these words. The goal of training is simple. Predict the next token after the context window. This is called next token prediction, and it's the core of how LLMs learn. The 4 input tokens are fed into the neural network. The network outputs a probability for every possible next token in the vocabulary. In GPT-4, that means predicting from 100,277 possible tokens. For example, it might produce on with a probability of 1%, because with a probability of 3%, and with a probability of 2%. So in this case, the network predicts because with the highest probability, but the correct token in our dataset is actually with. Now it's learning from mistakes. Because we know the correct next token, we can compare the network's prediction to the true answer. We then calculate an error and update the neural network's parameters to improve its predictions next time. This process is known as gradient descent. Optionally, if you'd like to dive deeper into the gradient descent algorithm, you can check out this Wikipedia page. So, initially, the network's predictions are mostly random because its parameters, or weights, are randomly initialized. The training setup is called self-supervised learning because the tokens, aka the labels, come directly from the data itself. So, the next time the model sees a similar sequence, it's more likely to assign a higher probability to with, which is the correct answer in this context. This cycle, sampling a window, predicting the next token, comparing to the actual answer, and updating the weights, is repeated millions or even billions of times across the training data. With every update, the model gets a little better at predicting what comes next. Over time, it builds an internal understanding of how language works. To speed up training, this process is done in batches. Many sequences of tokens are processed in parallel using powerful hardware like GPUs and TPUs. This parallelism makes it possible to train models efficiently even on massive datasets. Let me tell you a few words about GPUs and TPUs. A GPU is a graphical processing unit originally built for gaming. But today it's used for deep learning because it can do millions of tasks at the same time. Great for training models. To give an idea of performance, a high-end NVIDIA GPU based on the Blackwell architecture can perform quadrillions of floating point operations per second. A quadrillion is equal to 1,000 trillion, or 10 to the power of 15. That's why companies like NVIDIA have skyrocketed in value, because they power the AI revolution. A TPU is a tensor processing unit. It's a special chip designed by Google specifically for machine learning. It's even more optimized than a GPU for tasks like matrix multiplication, which LLMs use a lot. This is an example of a Google Cloud TPU data center. So whether it's a GPU or a TPU, the goal is the same: train LLMs faster and more efficiently. Once the model is trained, it can start generating text. That's called inference. The model takes in a starting prompt, which can be a few words or full sentences. The model then looks at that input and guesses what the next word or token should be, based on probabilities. It's kind of like flipping a weighted coin. The more likely a token is, the higher the chance it will get picked. That token gets added to the sequence, and the process repeats until we've got a full response, like this one. So what we covered? During training, a language model learns to predict the next token based on a fixed number of preceding tokens. This number is known as the window size, context window, or sequence length. In essence, training a large language model involves feeding it sequences of tokens and teaching it to predict what comes next. It learns from mistakes by updating its parameters using gradient descent. This cycle is repeated across billions of examples to build a powerful model. And to make this process efficient, it runs in parallel on specialized hardware called GPUs or TPUs. That's the core of how large language models are trained. It's all about tokens, prediction, learning from mistakes, and going it at scale. We are taking a break, and in the next video, we'll go into the next phase, which is post-training.